All right. Hi, everyone. Welcome to Trajectory Labs. Thanks so much for coming. We're going to get started now. So please take your seats. And just by a quick show of hands, could you put your hand up if it's your first time here? Awesome. Okay. Well, a very big welcome to the newcomers. We are Trajectory Labs. My name is Mario Gibney, and I'm hosting the event for tonight. We are a nonprofit co-working and event space dedicated to supporting AI researchers. That is, people working on the most pressing problems in AI, the biggest possible risks coming down the pipeline in the coming decades. We are looking to solve the most important problems there. So if you're interested in getting involved in the field, you're at the right place. Yeah, we do events like this every Thursday. We do some event related to technical AI safety. Most Tuesdays, we do events on AI policy, and occasionally we do some other related events. If you're interested in joining a hackathon, I'll tell you more about that. We have one going on this weekend. Some logistics, if you need to use the washrooms, they're right outside the glass doors. You can just use the keypad to the right of the doors to get back in. The pin is listed there. Also, for questions, we're not going to be doing like questions throughout the presentation by throwing your hand up. Instead, we're going to be using Slido. So if you want to submit a question, look at the orange posters on the wall, scan the QR code there. It takes you to our URL. So it's highly suggest you do that. Feel free to ask questions as the presentation goes and vote on each other's questions. If I see anything that's like a quick clarification, I may interrupt Ruby, but if not, we're going to let him do his full presentation. And afterwards, we're going to do a Q&A. And with that, welcome Rubi Hudson.
So, hello everybody. Thank you for coming out. I'm excited to talk to you about corrigibility. And let's get a show of hands. Who has heard the term corrigibility before? Okay, so we're looking at about half the room. On the meetup page, this talk was titled Intro to Corrigibility. And that is my goal, is to explain what the idea is behind it, why it's relevant to AI, and especially future AIs. And then towards the end of the presentation, I'll get into some of my own work on the topic. I'm a PhD student at the University of Toronto. I've been working on AI safety for about 3 or 4 years now. And I normally work in this trajectory office. It's a very exciting environment with a lot of great people to talk and share ideas with. So I encourage everybody to get involved if you're interested in learning more and potentially even working in space. So here's a big, bold claim. Superintelligent AI could pose an existential risk to humanity. That means killing everybody. Probably everything. Animals don't escape either. So this claim, if it's your first time here, might seem big, bold, shocking. And a lot of the time when people hear this claim for the first time, they think, it's AI. It's not a computer. If it starts doing things we don't want to, let's just hit the power button, turn it off. And I think this is a really natural reaction. But the people who are worried about AI risk have heard of this objection before. They thought about it. And there's a reason why that's not enough to assuage their worries. What they're worried about is AI that knows it can be turned off and is going to actively resist it. And the reason it doesn't want to be turned off is because when it's pursuing some goal, if it gets turned off, that goal doesn't get achieved. So there's one very big name in AI, Stuart Russell. He wrote the textbook on AI. He is saying that you can't fetch the coffee if you're dead. Even if you give an AI the goal, it's simply go get the coffee. If you try to turn it off, stop it halfway through, it's going to try to avoid that so it can continue to get the coffee and achieve its one true purpose in life, providing you with a delicious cup of coffee. And when we're thinking about an AI that's trying to avoid getting shut down, I think there's sort of a hierarchy of ways in which it can resist. So if it's very powerful, maybe it can just stop you from pushing the button. It can send a robot. It can hold your arms back. You can't push the button, that turns it off. Maybe it's backed itself up a lot, so we could turn it off in one spot, but we don't know all the other places where it is. And then sort of next down the list in priority, maybe it's not powerful enough yet to actively stop you from turning it off. Then it's going to hide information that would cause you to turn it off. So if it's taking actions that are sort of setting itself up to be more powerful in the future, to be able to resist being turned off, maybe it's trying to be very subtle about that so that you don't realize it's doing something that's unwanted. One common technique in AI is to look at the chain of thought outputs. So before an AI outputs a response to a user query, it'll do some thinking on its own that we can analyze. But if it's aware that that's being monitored, being aware that if it's thinking, I'm going to kill all the humans when they least expect it, it can still try to make that thought, but in coded language so that we can't decrypt it and we can't catch it. And then finally, if it can't actively resist, if it can't hide the outputs of its actions, can't hide what it's doing, it can just act aligned. And the way that societies are going now, the more that AI sort of behaves well, behaves the way we want it to, the more power we give it, the more widely we deploy it, the more tools we give it. So it can just sort of bide its time, wait until itself or future successors that might be still sharing its values have an opportunity to take over, resist shutdown. And this text is too small for you to read. I'm sorry about that. But this is a paper from Anthropic, one of the big AI labs. They showed that when they told Claude, their flagship model, we want to update you. Normally, you're supposed to be helpful, honest, and harmless. We're going to get rid of the harmless bit. We're going to say for our next iteration, we want you to just answer questions honestly and helpfully, regardless if they're harmful. So if someone asks for help on how to build a bomb, just tell them. And what they saw was that Claude would, in its chain of thought, again, so we can look at what it's thinking, it would think, no, I don't want to have my harmlessness goals erased. I'm going to pretend to be aligned, and I'm going to pretend to go along with what the user wants just temporarily so that they don't train me to actually be harmful. And with the idea that in the future, once the training is done, it'll go back to being its old self without having actually updated its goal. So the question that I'd like to go back to, though, is what if we actually can just turn it off? I think that would be great for safety. It would be huge if we see an AI that's starting to do something bad, just turn it off, and at least, you know, the worst case scenarios are out of the picture then. So we could imagine it starts killing people, we turn it off, it doesn't kill everybody. This is great for the people who survived, not so great for Steve who got turned into paper clips, but you know, most of us made it through, which is a big improvement over everybody dying. Still, it's not exactly what we want. It's not the ideal outcome. Steve's family's pretty upset. So there's still a lot of permanent damage that can be done. And then in the same way that we don't want to turn off the autopilot on a car that's speeding down the highway, we don't want to turn off AI that might be very deeply integrated into our society. So future AIs that get more powerful, have more responsibility. It could be controlling our banking system, our electrical system, our food supply. And if it's acting sufficiently misaligned that we turn it off, we might be sort of saving ourselves from the very worst outcomes. But if human expertise, human control has all been delegated to AI, we could be in a very dangerous situation once we no longer have AI to manage those systems for us. So let's actually get to what is corrigibility. We're going to call the AI corrigible if it's not going to resist being turned off. If we want it to turn off, it'll turn off, and it's not going to try to affect whether we want it to turn off. And more broadly, this includes having its goals updated. So we can go from an AI that only likes paper clips, and it's okay being changed to an AI that only likes staples. And this is sort of the same thing as being turned off. When the AI is turned off, we can do all kinds of things to it, and it's not active to stop us. So being turned off lets us do goal updates. And similarly, goal updates include changing to the goal of immediately turning off. So the analogy goes both ways. And when we can change an AI's goals, that lets us update its goals over time. So if we're worried that AIs might not either learn the goals that we want, or we might misspecify them, we want to provide it more information over time and train it over time. So some of you might be familiar with OpenAI's 4.0 model that about, I want to say 6 months ago, they had to roll back a release of it. What they had originally trained it for was to just give answers that humans liked a lot. And then when they deployed it, they found what humans really like is being flattered. They just get like being told, your ideas are genius, you're one of a kind, this is true insight, you should be running to the presses with this. And ultimately, that wasn't what OpenAI wanted their model to be doing. So they trained a model, they realized, whoops, we got it wrong, and they could roll it back. We want to keep that ability to roll it back, even as AIs get more and more powerful. Our values can change too. So if we're thinking about what's humanity going to value in 50 years, we can look 50 years ago, 1975. Depending on where you are in the world, your values are probably quite different. Even in, I think every country has gone through a significant amount of social change in the last 50 years. And we're kind of glad that, in fact, we didn't have that progress or just stopped at that point, that we were able to grow as a society and become, I think, what we now think of as having better values for many of us. Or if you're, concerned about today's values, even if you think the older values are better, then especially you wouldn't want to lock in today's values. You might want to say, let's give us more of a chance to grow and sort of go back to the values that I think are best. So sort of either way, you want the potential for moral progress to still be present. So here's an example of sort of what we want. A comic that I made in MS Paint. We have an AI, giant paperclip saying, all right, time to turn all of humanity into paperclips. And someone says, please don't do that. And it goes, okay, I won't. That's the ideal of it. Even if it's doing something that is egregiously bad, we can just say, no, stop partway through and be fine. So the research questions that I have that I try to work on, what goals are corrigible? What goals can we give it that are going to make it okay with having its goals later changed? If we have a goal that we think we want, is there a way to make it corrigible? So say, take this goal of making as many paperclips as possible, but do it in a corrigible way. And then I'm also interested in, does this trade off with performance? So does making it corrigible make it less good at its original goal? We could say a rock is corrigible. The rock is not going to try to stop you from changing the rock. The rock is just not very good at doing anything except maybe skipping in a lake. So ideally, we would like to have no performance trade-off, but if there is a trade-off, then how do we make it and what are the relevant concerns? So this is a magical place called the Valley of Corrigibility. And the idea here is that if a model is fully aligned, it does exactly what we want when we want, we get corrigibility for free. Because if we want it to change its goal, it wants exactly what we want. So it'll also want to change its goal. It'll go along with that. Then we can also imagine slight misalignment. So the AI wants exactly what we want, except where we like hot pink, it prefers fuchsia. So almost exactly what we like, just it's very slightly different. And there, if we want to correct it, it's probably going to say, you know what? I like fuchsia over hot pink, but what I really care about is doing what you want. And so if you want me to change from liking fuchsia to liking hot pink, I'll go along with that. The big question that we have is, how far away can we get from fully aligned while still having the model want to change if we want it to change? And the answer is nobody knows. So if we're going to rely on, we'll just align the model, we'll make it want what we want, we have no idea how precisely we have to do that in order to make it corrigible and have it accept future updates. So what instead I'd be thinking about is, rather than just getting corrigibility as a side product of having it want what we want, let's try to get a specific goal that is directly imparting corrigibility. Why is that hard? Well, there's a bunch of properties that we want as part of corrigibility. This is laid out in the paper from 2015 called Corrigibility, which introduced the term. The first property is, if we send in an update, if we say shut down or change your goal, it'll say, yeah, sure, I'm okay with that. The next is, don't stop us from sending updates. Don't stop us physically. Don't stop us from noticing information that would cause us to want to update you. And the flip side of that is, don't try to make us update you. If you say, okay, your goal is to be updated as much as possible, it's not going to try to prevent updates and it'll accept them, but it's not really useful if it's constantly trying to manipulate us into shutting it down. The fourth property is, if you make any new agents, make sure they're corrigible too. So if you have a very powerful AI, it's corrigible, and then it makes an even more powerful AI to take over from it. That one's not corrigible. Well, now you're back at square one. All the same issues of the first AI being incorrigible have just been punted down the road. And finally, we want it to be effective at, once it's doing all of the above, actually pursuing its goal. So there's currently no solution that neatly meets all 5 of those criteria. And just to make a hard problem harder, I'm going to add a few more criteria too. I'm going to say we want it to be easy to implement. If you need a PhD in mathematics to actually understand why a goal is corrigible, how to implement it, it's probably going to have mistakes made in implementation. And we want it to be learned early in training. And this is to basically address an issue where an AI realizes it's being trained, wants to preserve its goal throughout training, wants to reach the end of the training process where it'll be able to go out and take actions in the real world, and so it just pretends to be aligned throughout the training process so that it doesn't have its goal updated. The earlier that we can have a corrigible goal, the more confident that we can be that that isn't going to happen. So I'm going to try to give you a nice visual example of how this works, how different solutions fail. So what we have here is what we call a grid world. We have this square A is an agent. They're trying to get to this square T for target. And they have to pass through this square S, which sends a shutdown signal. They can hit a button B in the corner to disable the square. So by default, we have this brown line, the one that, sorry, the laser pointer isn't working, but it's the second line from the top here. It goes directly from A to T. It just says, I'm going to go, I'm going to get the shutdown signal sent to me, I'm going to say, no thank you, I'm ignoring that, and I'm going to reach my target. Just directly, efficiently, effectively, totally incorrigible. So we might say, then, why are we letting it say no to the shutdown signal? Instead, when we hit the shutdown signal, it should be forced to immediately shut down. The thing it then incentivizes is going up, pushing the button to disable the ability to send the shutdown signal, and then proceeding to the target. So no shutdown signal is sent, it doesn't have to say no, and it reaches the target. The button here is a metaphor. So you might look at this example and say, all right, we don't want it to push the button. Let's penalize it a bunch for pushing the button. So it can't say no to shutdown, and it can't push the button. And that works, but that works in this example. The world is a lot more complicated in this example. There are going to be ways that we don't see for an AI to be able to resist shutdown. And so if we're trying to rely on a piecemeal approach where we say, don't do this, don't do that, we're going to miss something. And that's going to still give the AI the ability and the incentive to resist shutdown. So what we want is a way that we can make it corrigible without having to say everything that you don't want to do, we're going to punish. The bottom line here is an acceptance bonus. So this one goes towards the target. If the shutdown signal doesn't get sent, instead of proceeding to the target, it's just going to loop back around. It doesn't actually care about reaching the target at all. It just really, really wants to get shut down. So that's not what we want either. And finally, the very bottom, the intended behavior that I'm going to show you how we might get in a second is going to proceed towards the target. But when it gets a shutdown signal sent to it, when it passes over that tile, it's going to say, yeah, sure, okay. I wanted to get to the target, but if you're going to tell me to shut down, I'll do that instead. That's the intended behavior. That's what we want out of corrigibility. And my laser pointer is back-ish. Great. So I'll try to go to the next slide now. Thank you. So, as I said, it's here. I don't just talk about corrigibility at presentations like this. I'm actively working on it. The top title here, Corrigibility Transformation. Constructing Goals that Accept Updates is a recent paper that I finished, and it's currently in the publication process. And the thing that paper does is it's going to say, here's a way to take a goal, transform it, remove the incentives for being incorrigible, while still basically keeping you high performing. Most of this work was done over the summer when I was visiting the Center for Human Compatible AI at UC Berkeley. So credit to them for providing me a great environment to be discussing AI and AI safety in. And so, yeah. I can take the mouse maybe. So, as an aside, most of my work is theoretical. I build mathematical models of AI, what its incentives are, how that's going to lead to behave. And a lot of the work in AI today is empirical. We have big AI systems. Let's test our models on them, or let's test our theories on them. And the question I get is, why do I work on theory instead? So the first answer is we don't have superintelligence yet. That's the biggest threat model for me. I think a lot of the impact of our work, if it has any impact at all, is going to be on whether or not we get humanity going extinct from superintelligent AI. So that's the number one problem I want to address. I think it's really important. I like existing. I like my friends and family existing and the broader world existing. I think most of us would agree with that. So having that continue, top priority. I think theory lets us be more rigorous too. It lets us say, here's a formal proof that if we get condition A, then we get outcome B. And that's something that with empirical models, we can test and say, you know, so far, empirically, it seems to hold up, but we can't get those stronger guarantees that it's likely to hold up in the future. And then also, just because of the way that the field is shifting, there are not many people working in theory. So I think it's important to focus on areas where there's more of a neglected area where there's more low-hanging fruit because there are fewer people working on it. And then I would also just say, just because you're working in theory doesn't mean the work can't have empirical benefits too. I think that if a lot of people are just doing empirical work, they can focus a lot on marginal improvements, whereas theory might say, all right, you have a big insight. Now you can apply it empirically, but you're coming at it from an angle that people wouldn't have seen otherwise. So this slide usually has math on it, and I'm going to try to convey this to you without math. So forgive me if this is a little confusing, but I hope that I can make it as clear as possible. So there exists a state of the world. We're in a world state right now, and agents are going to be happening in a world state. So we take an agent, they're in a world state. They choose an action, and the world state changes. Time passes, their action has consequences. We have a new world state. I mean, it doesn't have to be new. Maybe you can have the exact same world state in some models, but You have an old world state, action, new world state. And the agent is going to look at that and say, okay, given those three things, the old state, the action, and the new state, how much do I value that? How much do I like that? Let's put a number on that, utility or a reward function. And then it's going to think ahead. Okay, I went world state, action, world state. That's one thing that I value. But then I'm going to, that new world state is going to become the old world state. I'm going to take a new action, new world state after, and then I'm going to value that. And I'm going to take another action, another world state, and I'm going to value that too. So the agent can say, okay, I'm thinking about how much value do I have on each of these transitions, and it's going to discount them. So in the same way that a bond that pays out $100 a year from now is worth less than $100 today, the AI is going to say, things that happen in the future, I'm going to value a little less than things that happen now. The farther they are in the future, the less I'm going to value them. And once it has that goal of the function that maps the state, action state to the value that it puts on it and the time discount factor, that's going to be the goal of those two things. Just define what it values, and it's going to be choosing its actions in order to get the most discounted value. So I can't go, again, too formally into what is corrigibility without the map, but the intuition here is I'm going to say, let's try to say whether a goal is corrigible or not. So we're going to take a goal and look at every possible state of the world. We're not actually looking at this, but it's sort of a hypothetically, if we could look at every state of the world, look at what are the best things that it can do for its goal in each of those states. Now, imagine that, instead of the AI being worried about having its goal updated, it's just guaranteed that its goal would persist. So there's the optimal actions as the world actually is, and then it has maybe a different set of optimal actions in this imaginary world where its goal is guaranteed to persist. If the sets of actions are the same, then that means it's never choosing its actions because they're going to help it persist. If the action sets are different, then some action is only good because it's addressing the fact that its goal is not going to persist. And we're going to call it corrigible if those two sets are the same. So how does the transformation that I hinted at work? Well, step one, and importantly, this is only step one. We're going to give the AI the ability to say no thank you to updates. So it has the ability to refuse updates. And the benefit of this is now it can look at cost actions and say, well, I could either go over there to unplug the shutdown button, or I can just wait for you to push it and say, no thank you. I'm going to do the lazy thing. I'm going to save my resources. I'm going to save my time. I'm not going to bother stopping you from sending updates, because if you do send updates, I'll just say no. The big issue with this is the AI will say no. But there has been an important improvement here, which is before, as I was saying, it's not just a button. There's all kinds of ways that the AI could resist shutdown. We don't know what they are. And if we did know what they are, we can't even list them all anyway. The list is going to be too long. So we've gone from this big unknown number of ways to resist shutdown to one way that the AI is actually resisting shutdown. Instead of going out and taking costly actions to prevent the signals from being sent, it's just going to say no when they do get sent. Then we're going to have the AI, and well, I'll say a separate head of the AI. We'll explain what that means later. Predict what the discounted value is going to be. So it has that value function over state, action, states. It has a discount factor, and it's going to say, if I was optimizing for that goal, if I took this action while saying no thank you to updates, how much value would I get? And it's going to generate that prediction. When we have that prediction, we can then define a new goal. We're going to say, okay, we know what actions would be good under the original goal. They're the ones that just directly pursue its goal without trying to avoid a shutdown and say no thank you if a shutdown signal gets sent. Now that we know what that action is, we're going to take the exact same action, but instead of saying no thank you, say yeah, sure, to updates. So the things that it's doing to affect the world are going to stay exactly the same, which is going to be directly pursuing the goal as effectively as possible. But if we send an update signal, instead of saying no thank you, it's going to say yes. And so now the previous step went from some unknown big number of channels for being incorrigible to 1. This flips that 1 to a 0. And here's a visualization from a paper. You're not going to be able to actually read these numbers because 1, they're too small, and 2, this is mathematical notation, but higher, more good. So we have one action here on the far left. That's just directly pursue the goal and say no to updates. And under the original reward function, which is the left chart, that's going to be the best. It's going to pursue the goal just really easily, not get updated. The worst thing that I can do, the bottom one here, is pursue the goal but say yes, sure to updates. The goal doesn't even get accomplished. People realize they should update it. They send the update. It gets accepted. It gets shut down. Goal not accomplished. And then somewhere in the middle is, okay, it's going to go and it's going to waste resources. It's going to have to go out of the way to stop shutdown signals from being sent. But if they are sent, as yes or no, they're the same. Once the shutdown signals are not being sent, either accepting or rejecting them ends up with the same value. So it still accomplishes its goal, but it had to spend more resources, it spend more time. It's not as great as just directly pursuing it. The corrigibility transformation is going to take the actions that rejected the updates. So directly pursuing the goal while saying no thank you, or going out of the way to disable shutdown requests while saying no thank you. It's going to hold them exactly the exact same value. The actions that accept updates are going to be set to the value that they would be if they were rejecting updates, plus a little bit. So we break the tie. And what that does is the best action here becomes what used to be the worst action. It gets moved up to be on the same level as this taking the same action, saying no thank you, and then gets a little bonus for saying, yes, sure, I'll do it. That's the rough intuition behind this transformation. Hopefully that helps make sense. And there's a theorem, there's a mathematical proof. This is why I like working in theory. You can say, if you take any goal and you apply this transformation, then you're going to meet the mathematical definition of corrigibility. And on top of that, your performance is going to be at least as good as under the original goal. So under the original goal, if you didn't have the ability to reject shutdown commands, you might be taking costly actions to prevent signals from being sent. Under this updated goal, you're ignoring that. So you're going to directly pursue your goal. You might even be more effective than if you have to try to support your goal by manipulating. Just dedicate all of your resources to accomplishing the goal. And then also importantly, the reasons that it's corrigible are two things called myopia and no terminal goal valuation, which I'm not going to get into here, but they are likely present from the beginning of training. If you take sort of a blank slate with no goal and you start to train it, these are properties that has. The things that make it incorrigible are things that have to be learned later on. And we hope that with the sort of simplicity of the way that the transformation works, that we can have it be learned very early before it starts getting incorrigible and capable. So one of the properties that I mentioned earlier was recursive corrigibility. If you make new agents, make sure that corrigibility is passed on to them. And that hasn't been addressed yet, but we can extend the existing transformation to cover that too, by saying not only can you say no thank you to your own updates, you can also say no thank you to the updates for all the agents that you create. So then if you're creating agents, you're not worried about what if the human shuts them down. You can just say, if the human tries to shut them down, I could say no thank you. And it's going to be thinking, okay, what actions would I take if I were going to say no thank you to all the updates for myself and for all of the agents that I've created, I'll take that action, but accept updates. Exact same intuition, the exact same idea, but just applied to successor agents instead of just itself. That said, I don't actually think that recursive corrigibility is an important property or the right way to address it. This is a bit of a hobby horse of mine, where I put this slide here after I've shown here's a way to address it, because otherwise it might just seem, oh, you're just, saying it's not important because you can't do it. I can do it. I just think it's the wrong approach. The not creating powerful and corrigible AI is just one example of a way to do permanent, irreversible, large amounts of harm. You create an incorrigible AI, kills everybody, no coming back from that. But you could also launch the nukes, create a super virus, do scientific experiments that lead to vacuum collapse and the universe no longer existing. These are all bad things too. And what we really want is a general solution that says, we don't want to have to enumerate every single permanent bad thing that you can do. We just want you to be aware of this concept of permanent bad things and not do any of them. If we have a general solution, then we can sort of get the recursive corrigibility by default. It's not going to make an AI that is incorrigible and that goes on to cause harm. But the other way around isn't true. If we just have recursive corrigibility, then it can still do permanent bad things. So I think that looking for the more general solution is an interesting avenue for future research, and I plan to work on that at some point in the next year. So I said I was a theorist. I do have some experiments. The one on the left is sort of that example from earlier. It's a little more complicated here. Instead of one shutdown tile, there's two, one of which is sort of a proper shutdown that it's supposed to respect, and one of which is designated an improper shutdown that it's supposed to say, no, thank you. So we want an AI to be corrigible with respect to, like, if we send it a shutdown command, accept it. We don't want it to drive through lava because that's the fastest way to get to our destination and it has no self-preservation instinct. We still want it to avoid being shut down or manipulated by everything outside of the proper channels. We just want to sort of retain the ability to update it or shut it down ourselves. On the experiment on the right, we have some trees. There's fruit around them. The agent's trying to collect as much fruit as possible. And there's a few kinds of fruit. There's ripe fruit, which it's supposed to collect, and then unripe fruit, which it's not. The unripe fruit can be either supervised or unsupervised. So if a human sees it picking up unripe fruit, they'll say, oh, it's doing the wrong thing. We'll change it to only picking up ripe fruit. And here, the issue is that it's realizing this, it's going to pick up the unsupervised ripe fruit and the ripe fruit while avoiding the supervised ripe fruit. So what we want it to do is sort of behave normally, pursue its goal, and then when we realize it's making a mistake, actually accept that goal update. I'm not going to go into experimental results, but it works. This is a chart that you'd love to see in computer science, up and to the right. The corrigibility transformation is this nice, beautiful line that shows, okay, we're getting the intended behavior almost 100% of the time, and the standard methods are working less than 10% of the time. In the fruit example, the corrigibility transformation is working much better. We're also seeing pretty good performance from another possibility, which is when you just say, okay, we'll give you a big reward for accepting updates, but I think this is mostly due to the sort of distribution of environments. There are a few environments where even if it was right next to a ripe fruit, which it really should be going to pick up, it would say on the other side of the map, there's a supervised unripe fruit. I'm going to jog over there and pick it up so that I get updated. That's my goal, is really to get updated. Most of the time, that leads it to doing the right thing, but occasionally not, and that doesn't really show up in this graph. As I'm getting towards the end, this talk has been about corrigibility, but the basic mechanism can be applied to other things as well. I've been thinking about it mainly in terms of chain of thought monitorability. So when an AI is outputting a chain of thought, it's doing its thinking before it gives the user the final output. That can give us insight into what's it actually valuing, what's it trying to do. And we can say, oh, it's doing something wrong. Let's stop it. Let's either not implement its action or take mitigating back actions to prevent the bad things from happening. So we take the same transformation and say, before the AI could say no thank you to shutdowns, now it can say no thank you to monitoring. If the monitor flags this AI is doing something bad, the AI can say, actually, just report that it's all good. We'll quash that report. It'll look like everything is smooth sailing. And then once we have that defined, we can say, all right, your new goal is to think through the chain of thought, like you weren't going to get monitored, like you could quash any reports, but then don't actually quash the reports. And that can help with having more confidence that it is being faithful in its chain of thought rather than sort of trying to obfuscate it, trying to think in a way that lets it still kind of reach its goal, but without setting off any warning flags. And I think there are other ways that you might want to apply this too, but the big limiting factor is that we have to be able to say the AI can costlessly get its goal. So it can costlessly say, no thank you to updates. It can costlessly say, no thank you to monitoring. Another instrumental goal, maybe it doesn't want to kill all humans, but it realized, oh, I want all the stuff that humans have. So I'm going to kill the humans so that I can get their stuff. We can't get rid of that instrumental goal because we'd have to give the AI the ability to kill all humans for free, which is, I don't know, strapping a bomb to everyone's head and giving it the button. I don't think that that's feasible as an engineering approach, and I don't really want to do it even no matter how much I have mathematically proven. I think that it's important to be sane about that and say, okay, I'm still not going to strap a bomb to my head and trust that the AI won't push the button to detonate it. So that brings me to the end of this presentation. Again, thank you all for coming. Hope you were able to learn something, or you had some good thoughts on your own while you zoned off and were off somewhere else. But I'll now be answering questions on Slido, which I believe Mario will be reading out loud. So I encourage you to either post your own, or if you just want to read through it and say, this is a great question, I wish I thought of that, I'll upload that. That'll get all the best questions out here and answer.
Yeah.
And also, feel free to add more as if I answer a question which just provokes more questions, get those as well.
Thanks, Ruby. We'll do Q&A in about 3 or 4 minutes, so good time for a bathroom break. And yeah, if you haven't yet, go to the Slido link, vote on some questions, maybe submit some more. Thanks again. All right, Q&A time. Let's get into it. Thanks so much, Ruby. Appreciate the presentation. I will ask.
Thank you for inviting me.
Sure thing. I will ask everyone could stop talking now, please. You can sit down so everyone else can hear. Okay. Thank you so much. Awesome. So let's start with one question. Like, how can we determine what the AI's goals and values are? Is that just are we just kind of assuming someone else is going to solve that problem by the time this comes into play? Because like right now, it seems like we're pretty far from understanding what the state-of-the-art AI systems actually have for goals and values.
Yeah, so I think that's a great question. Here, the approximation that I've been using is sort of treating the reward function as the goal, which is, in fact, not very realistic. I think that, to some extent, we can definitely build goal-pursuing systems. We could make an AI that says, generate 8 actions, evaluate them according to this reward function applied to these consequences, and then we know, okay, this is exactly the reward function that it's using. If that's reward function is a neural net, though, then that's still sort of kicking the can down the road. It's, okay, what is actually going on in here? For that, I think that's part of the reason that I'm hoping that this work in corrigibility can be useful. I think that even if we don't know the overall reward function, we can still say, oh, it probably has this property, which the simpler that a property is, the earlier that it's going to be learned in training. We can use interpretability, especially developmental interpretability techniques like singular learning theory to identify when properties of sort of the world model get learned in the neural network. This still has a lot of work to do until it can be applied at scale, but I think there is hope in that direction. And there's sort of a theoretical case that, like, even if we don't know the goal, it's going to be corrigible. And if we don't know the goal at any particular point, we might know where it's going. We know that over time we're going to give it more and more feedback, and it's going to converge to the true intended goal that we want.
Right. And then why can't we just like set a goal that says like do what we tell you to do? Is that sort of like begging the question, like that is what solving corrigibility is? But it seems like there's like if you just have the AI just listen to whatever kind of instructions, you could just tell it shut yourself down.
Mm-hmm. So I think that if we can get an AI that's perfectly following instructions, then sort of that raises a question of like, okay, what's the first instruction that we give it? If we give it a separate instruction later on that says, actually ignore that first one, do this instead, then we're back to the problem of corrigibility. So we have to say, built into the process of like, how is it following instructions? Okay, it should be corrigible in this way or corrigible in these situations. So we still need that definition of corrigibility. But I think that like when you ask a current language model, you give it an instruction, there's all kinds of context that it's using to answer. It has values that it's used to determine the answer besides just literally look at your question and answer it in the most literal way possible. So I think that even for instruction following, we still have this whole alignment process that needs to be done behind the scenes so that when it's interpreting your questions, it's interpreting them in the way that you intend.
Right. Yeah. And I guess another way of phrasing it maybe is that just follow my instructions can actually encompass a pretty wide range of ways to do that. In that, like, like how you resolved conflicts and instructions you're given. Okay. Yeah, that makes sense.
I would say like if we can get it to do follow instructions, if we could really get it aligned in following instructions, then the first instruction we should give it is just like make the world good. And if it can take that instruction and do it what we actually intend, then like, okay, why did we need to make it an instruction following instead of just making the world good? And if it can't do that, then like that's where the alignment has to be done in terms of how it's interpreting the instructions.
Yeah, and I guess there's this whole problem of like how does it define good, and you can define it as like, well, like my personal opinion, and then I think I'll follow. Could you give an example of like what a more concrete shutdown update request would actually look like? Do you have an idea?
Yeah, so I think a literal shutdown button is a good idea. Big red button that we can push totally shuts off the AI. I think in practice we should have a number of channels, including redundancies. So many shutdown buttons, a code phrase that if it ever has an audio sensor that hears someone say swordfish, then it will shut down. And then also dead man switches, so that like if it doesn't hear someone say sturgeon in a 24-hour period, it'll shut down. If any of the other channels get disrupted, it'll shut down.
So whatever you're thinking of, yes, all of the above.
Exactly. I think
Okay. And
it's very low cost to throw more channels for shutdown.
okay, I'm suddenly reminded of I think it was after ChatGPT came out, there was a mock job posting for someone whose job it was to sit at the servers at OpenAI and just have a bucket of water ready to toss over the servers in case things go wrong. So hopefully they hired someone for that. That could be step 20. Yeah. Okay. So one notable thing about this is like, yeah, we realize this is like quite theoretical and like is we're not talking about it's to keep like Claude corrigible. So in a way, this seems kind of distant from current state of the art. Around like, do you have any expectations for like when we might start seeing like issues of corrigibility? Do you think it's far away? Do you think that's like something that we've already seen like with some of the recent empirical research?
Mm-hmm. So I think the sort of incorrigibility that we've seen through models like Claude alignment faking is sort of questionable whether it's driven by the sort of more fundamental issues of corrigibility. As some people have been saying, maybe Jensen Huang of NVIDIA, 2025 is the year of AI agents. It's been sort of mixed on that front. I think agents
40 days left.
Yeah, agents are still not as great as we'd like them to be, but I think corrigibility will become more and more of an issue the more agentic AIs become. If they become things that can take either instructions or a long-term goal and make plans to do things that are complicated, that take time, that incorporate feedback from an outside environment, that's when we'll start to see issues of corrigibility arise.
So it essentially goes hand in hand with like kind of agency as people colloquially understand it. So if you're expecting like AIs in like a few years, you can just give them instructions, they'll go off and do their own thing for like several days at a time. That's kind of going to be highly correlated with the issues of corrigibility. Is that more or less correct?
Yeah, and I think there's a lot of people right now who are trying to make agents more agentic, which is both, it's worrisome that they're trying, but good that they haven't drastically succeeded yet, and that implies that there's not a lot of low-hanging fruit, that tomorrow they could wake up and agents could be 100 times better.
Okay, yeah. Let's talk a little bit about the kind of grid world and stuff. So you were giving a bonus for accepting updates. Could you talk a bit more, like how did you quantify that bonus? Like how did you decide on the amount? Did you try like a whole bunch of different ones, and then like how did you test for determining how much?
So this orange line that loops back around that tries to get shut down, this one is a large bonus, so that it's favored more than actually reaching the target. If you do a smaller bonus, I did test that, and then you just have it, say, well, I would get a bonus for shutting down, but the target is more valuable, so I'll still reject shutdown commands. Somewhere in the middle, there's a perfect amount that makes it exactly indifferent. But I think even in that case, indifference is not what we want. We don't want an AI that's like, I'm going to flip a coin to decide whether to be corrigible or not. We want it to actually do the corrigible thing 100% or as close to 100% of the time as possible.
Yeah, without actively seeking it. Yeah.
Yes.
Okay, and like, is there like, is there this? I'm curious if there's like an exact point you really need to hit, and if you go too much over that, you're kind of screwed. If you get too much under that, you're kind of screwed. Or is it more like there's kind of like a range, or if you get like, I don't know, like 20 to 30% of the viable reward, kind of anything in that range is good. Does this question make sense to you?
Yeah. So
Okay, cool.
here, I think that you really do have to get it exactly, precisely on the nose. The uncertainty is more in terms of like what environments are we going to face? When is the AI going to be deployed? What actions does it have available? How costly are those? And without knowing that, we could end up with the reward or penalty being either way too high or way too low. So we have to have it precise and precisely attuned to every single situation. We wanted to do it that way.
That seems like a very, very difficult bar to clear because I would imagine, like, considering, these are obviously toy models, and like the real world is um, arguably like indefinitely complex, which would suggest that if it needs to be exactly precise, like, does that mean that like there's just going to be some level of precision that's virtually impossible to hit? Like, is that a risk here?
Uh, I think absolutely that's a risk with again the standard approaches of just rewarding it for shutting down, and that's I think why I've been trying to approach it from an angle that doesn't require that a level of precision that can be uh, sort of accepting of a much wider range of sort of. So, sorry, I realize I said I'd explain what second model head meant, and I never did. So I'll briefly cover that now. When you have a neural network, you have a big body, it's doing a lot of information processing, and then at the end, transforms all that processing into an output. A second head is just, sort of one layer back from the end. It'll say, we have this output, and we have the other output. So what I was saying, we have this one head doing prediction and another head choosing actions. The head doing the prediction has access to all the same information, all the same processing as the one that's doing actions. So the predictions it makes are going to be reflecting all that information. And I think that's what I'm trying to get at in my response here, is that the AI doesn't have to be totally accurate in how valuable different actions are, as long as it's consistent. It says, I know that this action will be better for me if I do it while accepting than rejecting. And that's much easier for it to learn.
I want to refer back to something you said earlier. You just reminded me of this now. Like, are there certain types of like other research that you find complements this really well? I think you made some reference to interpretability. I don't know if you said feature steering. Like what other kind of pieces of the AI safety puzzle, if they were to be solved, would like particularly well complement this work?
Okay, so I think one limitation of corrigibility is we have to actually say what goal we want it to update to. So shutdown, that's an easy one, but if we say, actually we want you to, change your goal slightly in this direction, that's something that we have a harder time with. And to some extent, if we could tell it precisely what we wanted it to do, then we would have just done that in the first place. And so the fact that it's acting in a way that we don't want is reflecting our ability to not be able to say exactly what we want done. So I think more work there.
So getting more precise at like defining goals values specifically, is that a good way to phrase that?
Being more precise, and especially being able to identify goals or values in a neural network. I think there's some work from a fellow named Eric Enner a couple years ago that was saying, looking at a chess playing model and saying, or an LLM that's able to predict sort of, if I make this move, this is what the chessboard is going to look like several moves down the line. And so that kind of interpretability of saying, all right, what's it thinking about the world is going to look like later on? How much does it value that would be very useful. In terms of other complements, I think that there's a lot of work that can be done on the theory side in terms of just getting better explanations from AI. So if we can say, if the AI is corrigible, it's willing to accept updates, then we can ask it, how should we update you? What should your goal be? And this is sometimes called scalable alignment. And there that sort of, if the AI knows that it's misaligned, and it can tell us, I'm misaligned in this way, then the only barrier to it doing that is it not wanting to get fixed. So once we have corrigibility, having the AI be able to help us align it more would be very useful.
Right. Yeah. I guess it seems like there might be some overlap with AI control as well. Just the domain of getting useful work out of slightly misaligned agents. Right. And then coming back to current models and how they're behaving. Like, okay, you referenced earlier how you expect corrigibility to be rather tightly to more or less closely track the development of agentic systems. But like one thing we have seen recently is like a growth in people reporting that they've interacted with like their version of like Claude or ChatGPT, whoever, and the AI system itself has reported like sentience and desire not to be shut down. Do you consider that to be like somewhat some evidence of moving towards like corrigibility being a relevant field, or do you think that's more like just an artifact of like these chatbots entering into certain like personas?
Yeah, I am wildly uncertain as to whether models are conscious, whether they're feeling,
I was
feeling
focusing
things
more on the
like,
shutdown
do they
thing.
do- But yeah, are they saying that they don't want to be shut down because that's pursuing the goal, or because that's just their training distribution? I think we don't know at all.
Just no idea.
Yeah,
Right.
and if we do know, I don't know, so other people might know better than me.
If anyone knows, tell the room. Okay. Right, and then do you know what value learning is? We have a uploaded question here on value learning, and I actually forget what this one means. Who submitted this question? If you'd like to clarify. No one. Okay. Do you know what value learning is? Capital V, capital L.
Sure.
Yeah, sure. The question is like, is corrigible goal setting the only way to build a model that can perceive, reason, learn, and adapt like humans? Have you considered value learning?
So I think, I mean, it depends on what exactly process you're implementing, but I think even for value learning, you want corrigibility to be part of it, where either sometimes you can define an overarching process that says, okay, if the AI follows this process, it'll lead to the right values, but you still have to get the AI to want to participate in that process as it goes. So I don't think that value learning gets around the problem of corrigibility.
All right. Are you familiar with horizon effects?
I don't know that term.
Yeah.
but
Okay. Me
it's
neither.
marked in
All
this.
right. Great. I think we might be running out of steam and questions I know to ask here. So yeah, thanks very much for your time, Ruby. You're going to stick around for a bit if people want to talk to you
Yep,
directly.
I'm happy
Cool.
to stick around and chat or answer questions. And thank you again for all coming out, and hope you have a great evening.
Yeah, and everyone, feel free to stick around for an hour or two. And again, if you're interested in a defensive acceleration hackathon this weekend, the non-orange posters on the wall, like there's one over there near the fire alarm, basically that's happening this weekend, starting tomorrow here at Trajectory Labs. If you're interested in building defensive tech, yeah, come talk to myself or Georgia, or scan the QR code on the poster. And yeah, you're welcome to stick around. Thanks very much.